Welcome to today's Explainer, everyone. Think of this as your own personal interactive calculus masterclass. Today, we're taking those two-dimensional integration concepts you've already totally mastered, and we're upgrading them to build reality in 3 dimensions. So grab your mental graphing calculators, because it's time to find some volume. So right off the bat, how exactly do we use calculus to measure 3D volume? Well, we all know the basic geometric formulas for a simple box, right? Length times width times height, or the standard formula for a sphere. But the big question for our lecture today is how we calculate the volume of really complex irregular shapes. I mean, without this specific type of calculus, engineers literally couldn't calculate the fuel capacity of a curved SpaceX rocket or the precise volume of a custom-machined engine valve. In our previous lessons, we used definite integrals to find the flat 2D area between two curves. Today, we're taking that exact same mathematical tool and upgrading it to solve massive, real-world engineering problems. Here's a quick look at our syllabus for this masterclass. We'll start with our welcome, move right into the slicing method, explore solids of revolution, tackle the disk method, upgrade to the washer method, and finally wrap up with your next calculus challenge. Let's get to it. Section 1. Welcome to Calculus class. This is where we put math in motion. Moving right along to Section 2, the slicing method. This is going to be our foundational toolkit today. All right, I want everyone on the exact same page, so let's firmly define our core vocabulary here. A cross-section is simply the intersection of a plane with a solid. Think of it like buying a whole, uncut loaf of artisanal bread. Every single slice you cut with your knife reveals a flat, 2D surface, right? Well, that surface is our cross-section. Now, if the loaf is weirdly shaped, every slice is going to have a totally different 2D area. And our goal is to find the mathematical formula for that changing slice. Because listen, if a solid doesn't have a constant cross-section throughout the whole thing, we just can't use basic geometry. We literally have to slice it up, estimate the volume of each individual piece, and then add them all together. Think about it this way. When we take a 3-dimensional cylinder and slice it perpendicular to its axis, it reveals a perfectly flat, semicircular cross-section. Now, in mathematics, a cylinder is defined, generally speaking, as any solid generated by translating a plane region along a perpendicular line. So because a cylinder is completely uniform, every single slice perpendicular to that axis is going to be identical. It's basically the absolute easiest scenario. But you know what? It proves our concept beautifully before we tackle the much harder shapes. Okay, here is your master strategy for solving these problems. Step 1, examine the solid and determine the shape of its cross-section. Step 2, find the mathematical formula for that 2D area, which we're going to call A of x. Now, let me pause right here, because this is where I see most students make a mistake on exams. Finding A of x requires you to express the radius, or the base of your shape, entirely in terms of x. Don't mix your variables. Finally, step 3, integrate over your given interval from a to b. And to find those a and b boundaries, you're often going to need to set your equations equal to each other and just solve for the intersections. And honestly, this brilliantly illustrates the absolute magic of calculus. We start by estimating, right? Adding up the volumes of a finite number of chunky slices, exactly like a standard Riemann sum, but the sheer magic of the integral is that it lets us slice that shape an infinite number of times until those slices are microscopically thin, giving us 100% perfect accuracy. As we take the limit as n approaches infinity, a Riemann sum turns into this exact definite integral. Volume equals the integral of a of x dx. It's beautiful. All right, section 3, solids of revolution. This is where we spin 2D into 3D. So if a region in a plane is revolved around a line in that same plane, the resulting solid is called a solid of revolution. Imagine a high-speed machine lathe in an engineering shop. If you take a flat 2D curve and spin it incredibly fast around an axis, it sweeps out a solid 3D object in space, something like a table leg, a custom engine piston, or even a rocket thruster. We are effectively doing digital manufacturing with calculus here, taking abstract curves and spinning them into real-world geometry. How cool is that? Which brings us to Section 4, the disk method. Time to use some solid disks. When we use the slicing method on these solids of revolution, it actually goes by a special name. Because our starting 2D region is completely flush against the axis of revolution, meaning there are absolutely no gaps whatsoever, every single slice we take perpendicular to that axis will form a completely solid circle, a disk. This makes our geometry incredibly straightforward because we don't have to worry about any complex inner cavities messing up our math. For example, take a parabola bounding a solid. We know the area of any circle is pi times the radius squared, right? Well, in the disk method, your radius is simply the height of your function, your f of x. So your integral just becomes pi times the function squared, dx. You literally just integrate that formula from your starting boundary to your ending boundary. And hey, quick professor tip for you. Always remember to pull that constant pi out to the very front of your integral right at the beginning. It will make the algebra significantly easier on yourselves later on. Section 5. The washer method. Dealing with solids that have cavities. Now, on an exam, you absolutely must recognize when to switch your tools. If your 2D region hugs the axis perfectly, great. Use the disk method. But what if there's a gap between your function and the axis of rotation? Well, spinning it creates a central cavity. You aren't making a solid pancake anymore. You're making a donut. And in calculus, we call that donut a washer. If your solid is defined by the region between two completely different functions, the disk method fails and the washer method steps up to the plate. Look at it this way. When a 2D region sits above the axis with empty space beneath it, revolving it creates a 3D shape with a hollowed-out center, kind of like a megaphone or a hollow cone. Because it isn't flush with the axis, our cross-section isn't a solid disk anymore. It's a circle with a smaller circle cut straight out of the middle. If you ever calculate this as a solid disk by mistake, you are going to end up with enough extra volume to accidentally build a 4D donut. And I assure you, a 4D donut will definitely not get you full credit on my final. So here is your master formula, and please pay close attention here to avoid the most common mistake I see in class. To solve this, we find the area of the massive outer circle, and we subtract the area of the empty inner circle. Your top function, f of x, is your outer radius. Your bottom function, g of x, is your inner radius. You must, and I mean must, square them individually before subtracting. It is f of x squared minus g of x squared. Do not, under any circumstances, subtract them first and then square the result, or your math will completely fall apart. Almost done. Section 6, your next calculus challenge. Let's look ahead. All right, class is dismissed. You've successfully learned how to turn 2D graphs into calculable 3D reality using slicing, disks, and washers. Huge accomplishment. But I want you to leave thinking about this challenge for our next explainer. What if our shape makes taking flat slices mathematically impossible? What if instead we calculate volume by nesting together rolled-up cylindrical shells, exactly like the layers of an onion? Think about it. Keep visualizing your math, practice those integrals, and I will see you in our next explainer.